Welcome to Linear Model. My name is Sarini Abdullah. I am the lecturer for this course. For this session, we will learn about first the general form of the linear model, second some examples of linear models, third some examples of nonlinear models, and the fourth topic is that how to linearize the nonlinear model. Now let's have a look at the general form of the linear model. If we have the target variable here only explained by one predictor variable, then the model representing this relationship is called a simple model. It is simple because it consists only one predictor, that is just one x. So this is the form of the model. Y is the response variable, beta naught is the intercept, that is kind of like representing the value of y whenever x equals 0. But sometimes we don't have data with x equals 0. In that case, we cannot interpret the beta naught. Otherwise, we will do some extrapolation, and extrapolation is not recommended in linear regression. Beta 1 here is the slope of the regression line that representing the contribution of x in the value of y. So here, if we change x by 1 unit, we expect that the value of y on average will be changed by beta 1 unit. And here we have the epsilon representing the error term. That is something that explains the deviation between the true value of y and with the predicted value of y using this model. And with the error, we have the assumption that error is normally independent and identically distributed with a mean of 0 and constant variance of sigma squared. Now, if the target variable can be explained by several measurements, in here let's say x1, x2 all the way up to xp, then it is called the multiple model, and it takes the form of something like this. So y equals the intercept plus contribution from x1 all the way up to the contribution from xp plus the error that explains something that cannot be explained by x1 up to xp. And we have the same assumption about the error. Now we look at some examples of linear model. So here let's say we are given this kind of data, and then our mathematical background tells us that this is just a linear function. Y is a linear function of x. So it's just simple that we propose this model with this assumption. But the question is that, is this a linear model? To assess whether this is a linear model or not, we need to look at how much is y changed when we change the value of x. So let's say we change the value of x by 1 unit, represented by delta x equals 1. And then just doing a simple mathematical subtraction, we got the delta y equals beta 1. And here beta 1 is a constant. In that case, since the changes in y is constant, so we say that this model is a linear model. Now we look at the second example. So if we are given this kind of data, it is just are reasonable from our mathematical background, it tells us that there is an inverse relationship between x and y. So in this case, I'm trying to propose the model of this um, form represented by this formula. The question is that, is this a linear model? Then again, we need to check on the changes of y whenever we change the predictor variable. Remember, I'm saying the predictor variable, not x. So in this case, let's do a little bit of manipulation. Let's say 1 on x is our new x, our new predictor. So my predictor is x star. So then, if we change the x star by 1 unit, then a little bit of mathematical manipulation is just subtraction again. Get that delta y equals beta y. And again, since this is a constant change in y, whenever you change your predictor variable, then this is a linear model. Now we look at our third example. It is really clear in here that there is a quadratic relationship between x and y. So it's just okay if we propose a quadratic model in here. And again, we can say that this is a linear model. Why is it called a linear? I will explain it in another session, especially for higher order term model. Now, for this example, our mathematical background tells us that this data is having an exponential relationship between x and y. So then we just propose this model. Is this a linear model? Again, we should check whenever we change the predictor by 1 unit, how much is the change in the response variable. And then we get the change is this much. We can see that this is not a constant change. The change in y depends on where the x starts changing from x at one value to x to another value. So x from 90 to 91, the changes in y is different if you change the x from 100 to 101, for example. So then, because the change in y is not constant, depends on the value of x, then we say that this model is not a linear model. But if we do a little bit of transformation, like we apply the logarithm transformation on both sides, so we get this formulation, then we think of logarithm of y as our new response, that is y star. Then we can see if we change x by 1 unit, we get the change in our response is a constant. It means that this model is a linear model. So this is an example of how we can change or we can transform a nonlinear model into a linear model. Now let's see some more examples. Here, is it a linear model? With the same argument as before, we can say that this is a linear model. It's the same with this example. Although we have logarithm of y and logarithm of x, but using the same argument, we can say that this is a linear model. But with this one, we can say that this is not a linear model. It can be a good exercise for you to try to verify these three models, whether they are a linear model or not. So far, we have seen some examples of models that are considered to be a linear model and some models that are not linear models and how to turn a nonlinear model into a linear model. So it's a good thing for you to think of what is the meaning of linear in linear model.